Hi, my name is Regina Barzilay, and I'm a professor of electrical engineering and computer science at MIT. Today, I will teach you about AI. I will try to demystify this technology and discuss application of AI to healthcare. So let's just immediately jump in and start talking about the most common way of doing machine learning or doing AI in healthcare. And this type of learning is called supervised learning. The reason it is called supervised, because the machine is given examples of correct decisions from which it can learn how to reason. So let's look at a very simple, concrete example. Let's say you're given here a number of movies, and for each of these movies, I annotated them whether a particular user likes these movies or not. And let's say, for simplicity's sake, we would just take two judgments, either they don't like the movie or they like the movie. So the goal of machine learning is to induce a mapping from the movie, from this very, very complex object, like a movie where a lot of stuff going on, to a specific judgment by a user. And as you know, today, using Netflix, using Amazon and other e-commerce application, machines can do it pretty well. So let's see how they can do it. So what you see here is, again, the object and the label, +1, -1. So one way to simplify for the machine this complex movie into more understandable format is to translate it into a feature vector. So in other words, you can record different aspects of the movie that you believe correlate with the user's opinion. For instance, the first question that we may ask, whether it is an action movie or not, and if it is an action movie, we're going to put 1. We can also ask, for instance, is it European movie or American movie? We can ask, does it have nature scenes, and so on and so forth. So in other words, you're kind of coming up with a questionnaire, and now every movie is represented by this vector, which encompasses the answers to these questions. So again, a movie now becomes a vector, and when we're thinking about training, a machine is just given this vector representing each one of the movies in your training set, and labels +1 and -1. And what it has to do is it had to learn the mapping from these features into a specific labels. And once it learned this mapping, you can give to it a vector of any movie that this user maybe haven't seen. And your goal is to predict what will be user opinion about this movie. So now what I want to show you is to represent the same information in a more intuitive graphical way. So when I told you about the questions that you can ask about the movie, you know, I didn't limit it in how many questions you can ask about it. For instance, you can take the whole IMDb. But now for simplicity's sake, imagine that you can just ask 2 questions about each movie. So if you just ask 2 questions, then you can use a 2D graphics to represent this training set. So in other words, there will be 2 questions, 2 coordinates, and every movie becomes a point in space depending on the value of these 2 coordinates. And each one of them will come either with plus or minus label. So this is a graphical depiction of the same training set. And then the goal of machine learning, and there are lots and lots of different algorithms to do so, is to geometrically separate all the pluses from the minuses. And again, when the machine learning model does it, it actually doesn't know where the vector comes from. Does it come from the movie, or it come from some questionnaire related to a patient, and you're trying to predict the risk of this patient? It just sees these vectors, in this case in 2D, but in reality, they will be very high dimensional spaces with pluses and minuses. And here I'm just showing one example of possible separation, which is a straight line. It doesn't have to be so, but this is one class of separators, which puts in one side of the plane all the positive examples, on another side of the plane all the negative examples. So if you are now to look at this new Sherlock Holmes movie that we supposedly don't know what is users' opinion about this movie, since it's located together with all these pluses, it's located in the positive side of the plane, you can say that for this specific movie, the label is plus. So what we've done here is something very powerful, because we can take now any point in space and predict whether it has positive or negative label. Of course, there is certainly accuracy of this decision, and we need to assess whether this accuracy is satisfiable for our application. So for those of you who still remember, linear algebra from high school, you remember that the slope of this line that you just seen is actually is determined by relative weights of the first and the second coordinate. Since, as I said to you earlier, we actually don't have just two coordinates, we may have very many different features. So in this particular case, a classifier that I showed you, which is a linear classifier, what de facto does, it lends the weight, how important is each aspect of the movie, how much it contributes to, let's say, positive judgment about this movie. So in other words, we don't need to say that it is important, that it is an action movie, or that it is a European movie. Provided sufficient amount of training example, the model can learn it automatically. And now you can say, wow, this is really a miracle, because the model just have these features, it has training data, how does it learn? And here, this particular drawing that I show you, it's called the learning curve. It shows to you how the performance of the model changes, and this is a very typical depiction, how the performance of the model changes as a function of the training size. And you can see here that, for instance, the model doesn't do great when it's trained only on 100 example. However, it is trained on 500, the performance actually becomes really high. And you can also see that maybe it is not worth to add extra effort to move from 500 to 1000, because it kind of asymptotically converges to some number, and the model is not data hungry at this point. So this type of understanding using learning curve helps us to decide how much training data do we need to train the model. I know that each time when I give a talk, people ask me, can you give me a formula? How many training examples do we need as a number of features, the size of the feature vector, and so on? There is really no formula for that, even though there is a lot of theories that studies generalization in machine learning. But this type of analysis can kind of demonstrate to you how much extra data do you need if your performance is not what you want to have? Because it could be that the model doesn't perform not because it is data hungry, but just because it was not, correctly designed and so on. But again, here to remember, it's like an exam. If you want to perform well in the exam, you need to see a lot of training examples, and it's really hard to do well if you just seen very few examples. The question, there are lots and lots of problems in clinical care that can be modeled as a supervised learning. For instance, when we're thinking about sepsis, we want to know which patients are likely to progress to sepsis, or you want to know whether this patient is going to stay on the prescribed medicine, giving all the information about the patient. So there are lots of examples, but the first thing you need to do if you decide to use supervised learning is to convince yourself that there is a pattern in the data. And like extreme case of no pattern in the data actually learned when I gave this talk to some audience, and somebody asked me whether we can apply supervised learning to learn how to win a lottery. So in this case, assuming that the numbers, the digits on the ticket are random, it's very unlikely that supervised learning will succeed. The second thing, you need to decide which features to use. Because when you're thinking about the patient, what information do you have? How accurate is this information? Because this information should be available automatically. And I want to say that in contrast to statistical models that maybe many of you are familiar with, this model can compensate for extra features because it will just learn that they don't correlate with an outcome. But if important feature is not there, it may really decrease the performance. Finally, we need to be very careful when we are collecting annotated data, and I will show you some examples where such collection was not done correctly, and it resulted in very negative outcomes. So despite the fact that, data collection may sound like a boring enterprise, it's really important for the performance, because this is the main source of knowledge for the model. And finally, it's really important to evaluate the model. I will show you some regimes where you can artificially get your performance extremely high, but while the model is still very, very weak. And of course, this type of models cannot be really moved for utilized on patients. Today I just want to say what I show you is a linear separator. It's like a line. Many times you want to have much more complex separators. This type of separators are achieved with neural models that we've seen, that currently are used everywhere on your iPhone when it recognizes your face, or in Netflix when it recommends you a movie. So what you see here, it's exactly the same feature vector as we've seen in the past. And this is different computing units which in a linear fashion combined all these inputs and this way kind of transform one vector to another vector with some component of nonlinearity. So I would not even try to teach you, in 5 minutes neural models, but the way to think about them, they consist of multiple layers of computing units, which are, each one of these computing units is very simple, but when you combine them, parallelize them, and make them work in a coordinated fashion, they can really identify very complex patterns, way more complex than each one of these individual units. And the reason they're called deep, because you have multiple layers. So traditional networks that would be used today may have hundreds of millions of these parameters. Parameters are the numbers that stay on these different edges, and that's why they require so much data for training. But I want, of course, I can just say these models achieve the best performance, but I just want to highlight one feature of these models, which is really important for our thinking, how to apply them for medicine. So I'm sure that many of you, since you went to medical school and I didn't, know a lot about, early vision. And you know that when we are looking at the cells that recognize objects, that they are organized in hierarchical fashion. The low-level simple cell identify edges, more complex cell identify simple parts, which are combined into a more complex patterns, which are then augmented with hyper-complex cells into objects and scenes. So what's very interesting about deep neural networks, that they actually do something similar to that. So here I am showing you a network that is trained to recognize faces. And the only thing that this model had is just example of faces. Nobody told to this model that a face actually has eyes and ears and lips and so on. But if you look which type of images activate, what kind of patterns each kind of layer of the network lens, you can see that the very low layer of the network lens very simple pattern. As you go to the second layer, something remarkable happens. It actually lens to identify parts of the face. Again, even though it never knew that the face consists, of eyes and nose. And then layer 3 actually takes these different parts of the face and learns how to assemble them into a coherent face. So why is it important? And we'll talk about it more, that it kind of tells us that maybe sometimes it is not our job to provide biomarkers to the model. Maybe the model can directly train itself to identify certain clinical situation from the data with outcomes. And I will show you more examples about it. But in general, let's go back to our clinical matters and think about it, with this new lens of supervised learning. Again, today we have a lot of information about the patient. It can be their mammogram, it can be their pathology slides, it can be their sequencing. And what you want to do is to take all these different available data and predict different, different questions that you may ask. Is this patient likely to get recurrence? Would they be sensitive to tamoxifen? Who is a population at risk? And again, given our training data, because we have in every hospital lots and lots of breast cancer patients with a known outcome, we can try apply supervised learning to answer some of these questions. And now, if I am looking at the landscape of AI method in healthcare, I will divide them into the three categories. So the first one, the blue one, is automating tasks that humans can do. This is the case where today we have personnel that can do it, but if you bring machine in, it's going to be cheaper, it can be more consistent, it can be faster. The second task is actually the second class of task is actually the most interesting. It's automating tasks that humans cannot do. There are lots of predictions when we are looking especially on cancer patients that we really cannot know what's going to happen to the patient. And the big opportunity here is to train the machine to make this type of predictions. And finally, and this is maybe the smallest area, but slowly emerging, is deriving new insight. When machine learns something, can you actually understand something better about mechanism of action or about the nature of the disease? But again, this is yet emerging area. So I will primarily talk about the blue and the green boxes. So let's start with example of automating the task that human can do. As you know, a lot of information about patient is recorded in the form of text, in natural language processing. And that's why whenever you do clinical trials, you need to have a coordinator who will take this information and translate it into understandable way that you can process, or even cancer registries in this country, again, they're done manually. Before machine learning, several people in here have a slide from Kevin Hughes that demonstrates to us it's actually not trivial to extract this information even from pathology report, because there are many different ways our pathologists, like Shakespeare, can use many different ways to say exactly the same diagnosis. So we cannot just write the patterns. So we build the model, and here you can see a reference to the paper where we can take pathology reports and extract around 25 different characteristics of the tumor fully automatically. It was developed on the patients from MGB. It has very high accuracy. And let me show you just one example how you can use this type of database, which was done fully automatically. I'm looking, for instance, at papers in New England Journal of Medicine and in JAMA regarding atypia, a popular topic of study in breast cancer community. You can see that in New England, for instance, the paper only looks at 674 cases. And you may ask why this condition is so common. And the reason is that they selected the population of 10,000 women, and they had manually curate them to identify who only had atypia and didn't have cancer. So at the time when we did the study, we just extracted, put exactly the same criteria, specific type of atypia, no prior cancer. And we can immediately identify 6,000 patients and study them with just few simple queries that clinicians can do. So here we can see that taking the data and translating it into easy to process format can really change the scope of our studies. See, another big area is, of course, cancer detection on the radiology images. I'm showing just one example. And this particular paper demonstrates that, at least in Massachusetts General Hospital data, the model works pretty well. But while we're talking about this kind of automating this task, I want to make sure to mention that there is a very common but dangerous myth that going among the clinician, and here I am referencing one of these clinicians who put it on Twitter. You can, or in other places, you can find out who it is. And in this case, he kind of saying you don't have to be computer scientist or data scientist. If you are so inclined, you can just go and do your own AI. If you can just download the tool and run it on the patient data. So this cannot be further from truth. And the reason is not because there is something, not right with clinician, but there is something not right with machine learning. It's still not at the point that you could use it the same way as you are using your iPhone, directly download the tool and utilize it. And I want to demonstrate it to you performance on 5-year risk prediction. You can see here, we're talking about the model trained on images to predict risk. I will talk more about it later, but the point is that if you're just taking out of the box model, you go and download generic computer vision tool and you train it on mammograms, your AUC is going to be 0.57 when the random is 0.5. If you're just doing generic improvement, which I would assume any, qualified machine learning engineer can do, you get to 0.79. However, if you're doing a customized model, which are designed for, for analyzing breast cancer data, you can get to 0.88. So I hope that this graph really demonstrates to you the importance of using the best model possible when we are processing patient data. But now I really want to talk about automating tasks that humans cannot do. Again, lots of tasks that we really care about are beyond our capacity to predict. Because each one of the human clinicians, maybe you see 10,000 patients in real life, maybe 50,000, but machine can be really trained on millions of patients and images, and it can remember all these data that you're feeding into it. So, and specific tasks that I want to talk about is predicting future breast cancer. So what you see here on the left is an image of a woman, and in this case, it's my own image, which, is classified to be benign at the time the image was taken. However, in 3 years, you can see that it progresses to DCIS. So the question that we ask, can you look at the original image and predict whether this patient is going to progress? I wanted to compare with, models that is commonly used today in clinical care, and it's called therapeutic. I'm sure you're all familiar with it. So if you're looking at C index on 5-year prediction, you can see on the cohort where we tested, our model is called Mirai, it achieves 0.77, while therapeutic achieves 0.63. So it's clear and significant benefit. And I'm putting here a reference to Science Translational Medicine that describes the study in details. And I would say that since we published the study, it was originally done in 3 countries. Since then, we expanded. So you can see that we tested it on a diverse population, including Asian, African American, Latinos, both within the United States and outside. And you can see that the results are very similar across all these different population. And, just 2 weeks ago, we published this result in Journal of Clinical Oncology. So this is a good news. And also you can see here the collaborator on this study, Dr. Connie Lehman, who is the head of breast radiology at MGH, actually utilized this model to identify high-risk patients during, COVID restrictions, when not the whole population, you couldn't screen the whole population. So by identifying the patients that needed extra, that needed to be screened without delays, you can make sure that patients who need screening actually get the screening. But let me just think with you aloud. How can we identify, just looking at the image, the future cancer? It just sounds as if we're reading on the tea leaves. So the first thought that comes to mind is like, density is doing something like this, and I totally agree with you. Density tries to do that. It tries to see what are the patterns in the image that are predictive of future cancer. However, we can look at traditional kind of risk assessment model, and we can see that if you add density, you get some boost, but it's relatively limited boost. And one of the it's clearly there is something in this biomarker, there is no doubt. And here we did the analysis on 200,000 patients from MGH, and you can see that in non-dense women, you have 6 out of 1,000 cancer, and in dense women, 8 out of 1,000 cancer. But at the same time, 42% of the population, at least in that cohort, has dense breast. So it's really hard to do something meaningful when you're saying almost to half of female population that they're in high risk. So what I would suggest that instead of using like human intuition or human whatever, when we are determining, when we are talking about breast density, to say, forget about it. I'm just going to give you an image and I'm going to tell you what's to happen in the next 5 years. You know, did this woman get or didn't get cancer, in which year she got cancer? And from there, I want to learn. So the question is, how do we define outcomes? How we can ensure that the model generalizes, that even if you train it on MGH population, it can work somewhere else, and how we can interpret these models. And the way, and there is a lot of clinical debate how to define the outcomes. For instance, you want to know, maybe it is enough to say whether it is cancer or not. Maybe you want to be able to say whether it's very aggressive cancer. Maybe you want to predict whether it is hormonal positive cancer, because then you can do chemo prevention. So there is a lot of options here. And of course, deciding which one to select will depend on how much data you have and whether your predictions actually clinically useful. And here, I want to, as a warning, to give you an example of the case where this type prediction, this type of annotation went horribly wrong. I don't know if you've seen this paper in, I think it was in Science, where the model that was trained in the hospitals to identify patients that are going to escalate, you know, because they're really sick and they need special triage. This model will take the data when the patient arrives to the hospital and predict whether they're in this special very sick category. So researchers at Berkeley found out that this model was significantly racially biased, that if you take two patients with the same clinical and demographic features, depending on the race, they will be categorized differently. And the reason it happened had to do with how the labels, how the annotations were created. They demonstrated that the way training data was labeled was using ICD-9, assuming that the patient who got very expensive treatments are the ones who need extra care. But clearly, given, you know, socioeconomic disparities in this country, there were a lot of patients in that population that, you know, were very sick, but they didn't get the right care. And the model inadvertently lent this type of bias. Another point that I want to bring was actually discussed in the New England Journal of Medicine, when they talk about another type of bias that, you know, many times when clinicians are kind of analyzing an image, let's say pathology, you know, some of the clinicians may overdiagnose, some underdiagnose, and whatever bias the clinician had who annotated the images, that's exactly the bias that the model is going to pick up. So the next important question is how we can ensure that that these models generalize. And this is really a big and important question, because the public is really concerned that AI can worsen health disparities. There is a lot of you know, discussion about it, and this is not surprising, because for you know, when I presented you with the machine learning, kind of supervised machine learning, I didn't explicitly say one important feature of machine learning, that the assumption of all these mathematical models is that you're training and testing data. So you train the model and you apply it to the new population, that they come from the same distribution. It's not the same patient clearly, but they come from the same distribution. But what happens is that we actually are applying it typically to a different distribution. Maybe we train it on MGH, but now we're applying it in some community setting, or maybe we're applying it in a different ages or races of the patients. But then whatever performance we observed when we train and test it on the same distribution may not necessarily hold. And I want to say that, and I hope that you will remember this picture, is that what the models can actually do, they are really great in picking up what is called nuisance variations. And, this is a funny picture, so hopefully it will stay in your mind. So what happens if you take the top computer vision model and train it on this monkey, or train it on to recognize animals, it has no problem identifying monkey as a monkey. But at the moment you're going to add to this monkey guitar, it starts identifying it as humans. Why? Because every single time in the training data, when guitar was there, you've seen a human. So the model uses as a guitar as a clue that it's actually there is a human nearby. And you can say how common are these nuisance variation all the time. Again, changing in demographics, changes in clinical setting, changes in devices. And we all know that bias was always there. For instance, when we, applied our QSIC in the standard form to MGH data, we've seen, it doesn't perform well on any of the subpopulations. On white women, it achieves 0.64, not great, but you can see that when we are looking at other subpopulation, African-American women and Asian women, it really gets close to random. The good news, the Mirai model, our deep learning model, because it was trained on the diverse population, actually performs comparably well on all these different cohorts. And as I already demonstrated to you earlier, when we trained it in 7 different institutions with very different population, it maintained performance. And again, the reason is that we really worked hard on creating the right training data and the right algorithm. And then another important question is how we can interpret these models. So there is a lot of question about, are these models interpretable? So I can tell you that this model can be interpretable. For instance, if you train your model to identify calcification, and then it will circle you the part which has calcification, the model can do it. It can produce you something like heat map and say to you where it looks when it makes a prediction. But the problem is that many times, in many tasks that you're looking at, like predicting future cancer in 5 years, humans cannot do it. So even if you are going to show it, what is a heat map, what the models look at, you still cannot interpret it. So my point is that as this machine learning becomes, and AI models become smarter and smarter, and as they can do more complex predictions, it would be harder and harder for them to explain to us what exactly are they looking at. I mean, they can explain, but we would be unable to verify. And what I want to say is, this brings us to this interesting question. Because this technology is very powerful and it uses different type of knowledge that we as humans do. And the question is how we can create clinical pipelines where you can utilize the strengths of clinicians and the strengths of this tool to benefit patients. And I would like to conclude my talk by saying that today, there are lots and lots of great algorithms, and this area continues to add more algorithms. Where I see the place of opportunity, where the things are lacking, is actually bringing this algorithm into clinical care, designing safe protocols, analyzing how it really changes patient outcomes, if it does. And I really hope that my talk gives you some idea and you will be interested to explore more and to contribute to this a growing field. Thank you very much for listening to me.